AP Chemistry. This is the answers video for the day 54 lesson on equilibrium constant. So this is our first lesson in the subject of equilibrium. And what equilibrium deals with are chemical reactions that don't go all the way from reactants on the left to products on the right, but they tend to stop somewhere in the middle. And there's still some reactants left on the left side, and there were some products made on the right side. Sometimes almost all the reactants go to products in these reactions. Sometimes almost none of the reactants go to products, and it can be anywhere in between those two. So that's the nature of equilibrium reactions. So what we're going to do is figure out what determines equilibrium and how it can be changed. All right. So on line paper, copy the 6 ways a kinetic rate law differs from an equilibrium law of mass action. The slide can be found at minute 22:43 of the lecture video. So go ahead and do that on line paper. Part of this assignment you can do on this sheet, and part on line paper. You'll be required to do on line paper. Do the whole thing on line paper if you'd like, but you'd have to copy down these reactions. Okay, so go ahead and do question 1, question 2. So write the equilibrium expression. It's really called the law of mass action. We can call it equilibrium equation, equilibrium expression. Its formal name is the law of mass action. I do tend to use that, but just understand when you hear that, it is the equilibrium expression. So for the equilibrium constant Kc. Okay, so the way it's written is Kc is called the equilibrium constant, and you take the products and you put them on the top. And if it's Kc, it means a concentration. So square brackets means molarity. That's a unit of concentration, moles per liter. How much lemonade powder did you put in the water to make your lemonade? Okay. Then what you do then is you don't put the coefficient there, but you put the coefficient up as an exponent. And then on the bottom is the reactants. Squared. And that's the law of mass action. Now, let's just do something for a second so you get a sense of what Kc means. If we rearrange, multiply both sides by O3 squared, and this could be done for any of the reactions we're about to do here, times Kc, that would equal O2. So what you're saying is, if you take the reactants and multiply them by a very small Kc, then you'll get a very small number over here, a very small amount of products. If you take the reactants and multiply them by a very large number for Kc, you'll get a very large number of products. So the size of Kc basically tells you how much products you're going to get from your reaction, whether it goes more towards products or less towards products. If it's a very small number, most of the reactants will stay as reactants and very few will turn into products. If it's a very large number, then most of the reactants will multiply by that and turn into products. Okay, so Kc, the size of Kc tells you how much the reaction wants to go from left to right, from reactants to products. All right, let's go ahead and do another one here, right here. Okay, so that's the products, and you take the coefficient and make that an exponent here. And then over here is the reactants on the bottom. That has a coefficient of 1, so that just has an exponent of 1. If you want to write it, you can. Okay, so we'll go on. You can go ahead and do C. I'm going to do D. So what we have here is, remember this 2 plus here has to do with it being an ion that takes on a 2 plus charge. It has nothing to do with equilibrium. It's just a part of what that product is there. So again, the products go on the top. There's a 2 there, so we put it there. And then on the bottom, we have the reactant. No coefficient. However, the rule is, and this is in the lecture video, that if it's a solid or a pure liquid, it does not get included in the law of mass action. So that right there is not included in the law of mass action. I just wrote it there to show you the way we would normally write it. So I'm going to now erase it. So that is the law of mass action for this. This doesn't even appear anywhere in the law of mass action. Okay, let's do G. That one was actually done in I think E was done in the lecture video. Let's go ahead and do G. So we should have a double arrow here. All right, so Kc equals, no coefficients there, and down below, and no coefficients on this side either. Okay, like that. Okay, oops, I'm off screen. So that's what I wrote. So I wrote products up on top, no coefficients, so no exponents, reactants down on bottom. But if it's a pure solid or a pure liquid, water is considered a pure liquid, then you don't include it in the law of mass action. So we take that out. Okay, so you do the ones that I didn't do here. All right, let's keep going. Sample of hydrogen and iodine are mixed in a 1 liter vessel at a temperature of 430 degrees. The only significance of temperature is that it tells you that it's at a particular temperature. The temperature is not going to change. The number 430 doesn't go anywhere in the problem. It's just stated standard that you got to do these reactions, these problems at a specific temperature. Once equilibrium is reached, it is determined that 2.5 moles of HI and 0.25 moles of H2 and 0.5 moles of I2 are present. What is the equilibrium constant Kc of the reaction at that temperature? Okay, so there's the reaction right there. So let's go ahead and write the law of mass action. I'll go ahead and write it over here on the side. Everything is a gas. There's no solids or liquids here, so everything goes into the law of mass action. And the numerator is squared, and then we have these two. Okay, so there's the law of mass action. Now, we can plug in the numbers, but what we got to be careful of is what do square brackets mean? They mean concentration. They mean molarity. Molarity is moles per liter. Okay? So what they gave you is moles. If they do that, then they also gave you the size of the vessel in liters. You have to divide moles by liters, moles per liter. That's molarity. And the law of mass action is in terms of molarity, not in terms of moles. So if you have moles, you're going to have to divide by the volume, and that would be moles over volume. Moles per liter would give you the molarity. Now, it just so happens here they made it easy. They gave you a 1 liter vessel. Okay, so that means that 2.5 over 1 liter, 2.5 moles becomes 2.5 molar. So let's write that here. But it's not always a 1 liter vessel that they give you, so that's 2.5 molar. So that's a concentration that we would use in this equation. The other one is 0.25 for H2. So the 2.5 was the HI. The H2 also over 1 liter. So the number is the same, it just switches to molarity. But you got to be sure that you're working in molarity with these equilibrium problems, not in moles. Okay, so we'll just finish it out with the I2. So now you have molarity that you can now plug into this equation up here. So we're going to go ahead and do that. Sometimes when I plug in numbers, I switch to parentheses. That's what you would have to use on a calculator, is parentheses. Okay. So we have 2.5 squared x squared, and that gives us 6.25 divided by 0.25 equals, divided by 0.5 equals, and you get 50. So the equilibrium constant in this problem is 50. That's your answer right there. Okay, so now we're on to number 2. In the synthesis reaction of ammonia from nitrogen and hydrogen, there's the reaction. Kc is 9.60 at 300 degrees. Calculate Kp for the reaction at that temperature. So you're given a formula in the lecture video. Let's go get that formula, and that's what we're going to use. It's simply then plug in the numbers. Okay, and this is in the lecture video for day 54. So they're giving you KC and they're asking you for KP. So you're going to use the formula on the left, and that is KP equals KC times the quantity RT raised to the delta N power. So let's go ahead and write that down. Okay, so over here we'll write it KP Okay, so Kc we're given right here. R is the gas constant. Now you may remember there's two of them. There's one we use with PV equals nRT, and there's one we use with a few other formulas. This is the PV equals nRT one, so it's R equals and you know what? I'm not even going to do the units of measure because Kp is going to end up being dimensionless. There's no units of measure. So rather than clutter up the page with the liter atmospheres over mole Kelvin, I'm going to leave it. Okay, and let's go over here and let's write down T. So they give you T in centigrade, but it has to be in Kelvin. Why? Because this is where the units are important here. Liter atmosphere per mole Kelvin. The units of measure for temperature are in Kelvin in this rate, in this gas constant. Therefore, you have to use Kelvin in this formula. So the formula for Kelvin temperature in Kelvin is 300, the centigrade temperature, plus 273. Okay, so we have this number, and this number. Then the delta N is the change in the number of moles. It doesn't matter what the substance is, it's just total number of moles on the reactant side, the left of the arrow, and total number of moles on the right side, the right of the arrow. So over here, I'm going to go ahead and put my coefficient of 1 there. We have 1 plus 2 is 4 moles. And over here we have 2 moles. So if you subtract that, you get a delta N, change in moles, of, it's really actually the other way around. It's delta N equals -2 rather. It's -2 moles. The number of moles decreased, in other words. It went from 4 to 2. So I really shouldn't put a minus sign here. I'll put an arrow. Okay, it went from 4 moles to 2 moles. That's a delta N of -2 moles. All right, so now we're ready to plug everything in. Now, I don't like to use double parentheses, so I'm going to put square brackets just as a second set of parentheses. The reason I need to do that is because this entire quantity, these two multiplied together, are then, first you multiply them and then you raise them to the delta N, which is -2. So the square brackets have nothing to do with concentration or molarity. It's just a second set of parentheses. So what you're going to do is multiply these two together, raise them to the -2 power, and then once you have that number, you multiply it by 9.6. So I'll go ahead and show you how I do that on the calculator. I hope it doesn't glare too bad. So I'm going to go 0.0821 times 573 equals, go ahead and hit the equal sign. I'm going to raise it to the power of negative, use that for the negative sign, -2. And hit enter, and there we get that number. Now I'm going to multiply that by 9.6, and it gives us that number right there. And I'm going to write that in scientific notation, so that's 4.34 times 10 to the -3rd power. No units, it's dimensionless number. Okay, so that's how you do that problem. Okay, so I'm going to go ahead and give you the answer for this one. You do have to do it and show the work. So the answer is going to be Kp. Okay, and that's the answer for this one. Go ahead and do that and show the work. Okay, number 4. All right, this is at the end of the lecture video, and it has to do with the 3 rules. It's very much like Hess's law, how in that you're combining 2 equations to make this equation, but what you do is totally different how you deal with these KC's and what you do to them. Okay, so what we're trying to do is we're trying to recreate this equation using these 2. All right, so the first thing we're going to do is we're going to look for something that only appears once up here and that's in the final equation. And what we see is that the 2HF and HF. So HF only appears once here. So that means in order to get 2HF, we have to do something to that. And what we have to do is we have to multiply it by 2. So I'm going to write that down here. I'm going to actually write the whole thing. I'm going to come bring it on down here. So we're going to multiply 2HF. And I'm not going to write the aqueous for all these. Okay, so we multiplied everything up here through by 2. And if you remember back in Hess's law with enthalpy, with delta H, what you would have done to that number there is multiplied it by 2, but you don't do that here. What you do is you raise the Kc, becomes that number 4 raised to the 2nd power. So you make that, remember how you make coefficients exponents in the law of mass action? That's what you do there. So that number becomes 16. All right, now what do we have to do down here? Okay, so we have H2C2O4 on the right side of our target equation. Again, that's my name for it. I like to call it that, the target. That's what we're trying to hit right there, recreate. And we have it on the left side here, but the number of moles is the same. 1 mole, 1 mole, it's just reversed. So what we have to do with this one is reverse it. So we're going to flip everything on this side over to this side. Again, this is just for ions. It has nothing to do with equilibrium. Okay, so we reverse that equation. And what do we do when we reverse an equation? Is in Hess's law, we would put a negative sign in front of that if it was enthalpy. So it's positive 12 would become negative 12. Not so here. Different rules. In this, what you do is you take the reciprocal. You flip it. Okay, 1 over 12. All right, so those are the 2 new equilibrium constants we have, concentration constants. So let's verify that what we did here does recreate the target. All right, so what we have is 2H on the left side of this arrow and on the right side of this arrow, so they're going to cancel. All right, so all we have left now are 4 things. We have 2F, and we have 2F there. We have C2O4 2 minus there, and we have it there. Over on the right side, we have 2F minus and 2F minus. And over on the right side, we have this. So everything matches up. It recreates. So now what we did is we added those 2 equations to get that. So now what do we do when we add those 2 equations? What do we do to these 2 numbers? We don't add them, we multiply them. Okay, so it's going to be 16. So the final equilibrium constant, in other words, for our target equation, for this guy right there, is going to be 16 over 12, which equals, reduce that 4/3. You can call it 1.33 if you want, but that's the equilibrium constant for the target. So it works very much like Hess's law in terms of how you do it, but what you do to the equilibrium constants is totally different than what you do to the enthalpies in Hess's law. Okay, so on your assignment down at the very bottom on the back, you were asked to do 4 problems from the book, the first one being 15.21. I was asked by a couple of students, do we have to do those? Absolutely, you have to do those. Those are the most important ones. It's getting you into these textbook problems, not just the ones I make up or copy from some source, and into the AP Classroom and the Princeton problems. Those are the ones that really look like AP problems, and that's what we need to do. Okay, so let's read this. So at 1,000 degrees Kelvin, by the way, you don't say degrees Kelvin. It's just a little quirk. but you say 1,000 kelvins. You say degrees centigrade, but you say kelvins. You don't say degrees Kelvin. If you do, it's no big deal, but that's just technically you just say 1,000 kelvins. Okay, and then they give you an equilibrium constant for pressure there. There they give you the reaction. It's all gases, which it has to be for pressures. Okay, and they ask you 3 questions. What is the value of Kp for the reaction? And they give you a reaction here. Now, it's a little hard to read this when it's kind of crowded in like that. That's like why when you write your answers, I don't like you to crowd them one line after the other. I like you to skip lines, and I think you should do that on the AP exam as well, unless you write extremely neatly. But even so, it's harder to read. So we're trying to basically compare this reaction with this one. So let's write them both down. What I would like you to do is you don't need to copy the problem, but I want you to write the relevant information on the lined paper. So I'm going to go ahead and do that. Okay, and then for part A, the reaction is this. And by the way, I'll go ahead and write this up here. Really should write. I like to write it to the right of the equation. So what they did here is they took this, they reversed this equation. Okay, you see that? So you reverse, which means you take the reciprocal. And that's going to equal 0.54. Okay, so that's the answer. Whoops, I was off screen the whole time. Sorry about that. Okay, there you go. Let me get myself on screen. Okay, so we took this reaction. In part A, they reversed it. They just flipped it around. That's reversed, so that means you take the reciprocal of your Kp. So your new Kp for this reaction, I should put equals Kp for that reaction, is going to be 0.54. Okay, let's go on to B. Again, keep a lot of space between problems. Don't crowd things together. Because I want to teach you to format your problems as well as how to just do them, but how to format them. You want to make it easy for the grader to give you points, and if it's hard to read your problem, your answer, then it's hard for them to give you points. So what is the value of Kp for this reaction? Okay, so they took this reaction, the original reaction, and they multiplied everything by 2. So the 1/2 O2 just became O2. And so what they did is times 2. So what does that mean you do to the, again, we go back to the original Kp, and the Kp, what you do to that then is 1.85 squared. You raise it to the second power, and that is going to get you 3.42. Okay, so that's the answer for B. Come on down to C. And in your book, you can read that for yourself. It says, what is the value of Kc for the reaction in part B? So they're taking this reaction, and they want to know what the value is for Kc. So what you do is Kc equals, okay, and we see a formula there. Kc equals Kp over RT times change in number of moles. So we're going to go back and write that down. Okay, so Kc equals Kp. Okay, and again, we're dealing with this reaction right here. So that equals 3.42. That's the constant you have to use. Temperature is given to you in Kelvin, so you don't need to make any adjustment there. And then we need to raise that to the change in moles. So here we have 2 plus 1. There's 3 moles on the reactant side, and there's 2 moles on the product side. So that's going to be a -1. The number of moles went down by 1. Okay, so we can go ahead and do this. Again, I would recommend you do it in pieces. So 3.42 on the top, and on the bottom is 0.0821 times 1000 equals, and then you're going to caret -1, raise it to the negative first power, and that gives you this. I can go that many digits out, okay, and then we divide that by 3.42, or we divide that into 3.42, and that gives us 280. 281 if you want to round it to that. Okay, the next problem you're asked to do is 15.23. It says the following equilibria were attained at 823 K. So again, they're just giving you a temperature to say, hey, it's at a fixed temperature, we're not changing the temperature. There's the two reactions. It says based on these equilibria, calculate the equilibrium constant for H2 plus CO2 produces CO and H2O. So this is another one of these Hess's law type problems. So what I want you to do is write these down on your lined paper. Leave plenty of space. You don't have to calculate or copy all the words. You don't even have to really write the 823 for all I care. It's just saying it's at a constant temperature. Really the relevant parts of this are these two equations and this equation. So go ahead and do that. Okay, so now we're trying to figure out what this Kc down here is for this reaction. Alright, so again, we go down here and we look for something down here in the target that only appears once up here. Well, this is cobalt oxide. It's a little confusing. That's cobalt oxide, that's carbon monoxide. That's a capital O, that's a little o, so be careful on that. That CO is totally different than that CO. Alright, so we need to find something that appears only once, and it looks like the H2 does. H2 appears on the left side of the arrow in the target, and appears on the left side of the arrow in equation 1. That means we don't want to change equation 1 at all. It's the H2 is on the proper side of the arrow, and it's the proper number of moles, 1. So we're done with that. So now let's go down and find something. Let's see, CO2 only appears once. It's right there. It's on the left side of the arrow. There's 1 mole of it. Over in equation 2, we see it on the right side. There is 1 mole. So what we're going to want to do is reverse this equation to get the CO2 on the left. Okay, and when we reverse, what we do to this is we flip it. So it becomes 1 over 490. And that equals 0.002. Okay, and after telling you not to crowd things too much, I crowded that pretty much too much. I normally would write this way down below. Okay, so there you got 0.002. So now let's be sure that these two reactions, so first I changed this reaction, so just so I don't get confused and use it again, I've already changed it, so I'm going to go ahead and cross it out. Now let's see if things appear. These two add up to this one. So CO2, we have CO2 here, and it doesn't appear anywhere else, CO2. We have H2 here, and it appears in the target on the left, nowhere else, so we've used those two. Okay, down here we have CO, cobalt oxide that is, on the right side of the arrow in this equation. Again, we should give it a name, equation 2A. So we've gotten rid of equation 2. So we have cobalt oxide on the right side and up here on the left side, so they cancel. Okay, we have cobalt here on the right side, and in this in the equation 2A, it's on the left side, they cancel. We have CO in equation 2 and nowhere else, so we use that, and there it is there. And we have H2O on the right side of equation 1 and nowhere else, so it appears there. So yes, our two equations, 1 and 2A, add up to be the target. So now what do we do when we add these two these two equations together, we take the K values, this should be Kc here, and we multiply them. So it's 67 times 0.002. So I'm going to just do that, 67 times 0.002, and that equals 0.134. Okay, we now move on to 1524, so consider the equilibrium, that equation in equilibrium. Calculate the equilibrium constant Kp for this reaction given the following information. Okay, so what they're asking us to put together two things that we did above. First of all, we have to recreate this reaction here using these two. And when we do that, we're going to find a Kc value. Once we have the Kc value, then we have to change it to a Kp. So it's kind of a two-step problem. Okay, so let's go ahead and again write down all the relevant information, meaning the equations. Again, the temperature. The temperature is significant this time because you're going to have to use it in that conversion from Kc to Kp. So I would definitely be sure to write it down. I would probably do it anyway all the time. So let's go ahead and copy this all down. Okay, just a couple of comments about this. This Kc of 2 means a fair amount of the reactants are going to go to products. Maybe half and half, not exactly half and half, but somewhere like that. But look at this Kc. That's a crazy big number. That means it's almost virtually going to go entirely from reactants to products, almost to the point where you would say it's not even an equilibrium. It is, because you can go both ways, but at whatever these conditions are, it's going to go totally from almost total reactants to total products over on this side. Now that's at that particular temperature. At a different temperature, it would be a totally different situation, and that would be a different Kc. It may not go that far from reactants to products. Okay, so first thing we're going to do is see what we can do here. So we have a Br. Be sure I copied this. Always check your numbers. And this should have been a Br2. So it's N2O2Br2 and 2NOBr. Okay, good. All right, so we have a Br2 on the left side of the target and on the left side of the equation 1, and it's this correct number of moles, 1 and 1. So it means we don't want to do anything to equation 1. We know that right off the bat just because of that one reactant right there, okay? Okay, so we see the Br2 is on the left side target, the 2NOBr right side target. So equation 1 is good. What about equation 2? Well, we have the N2 and the O2 on the right side of equation 2, but it's on the left side of the target, so we're going to have to reverse equation 2. Call it equation 2a. Okay. All right, so we've done that. And what that means, what we need to do is take the reciprocal of this very large number, which is going to be a very small number. And that's going to give us 4.76 times 10 to the negative 31st power, a really, really small number. Okay? All right. So let's go ahead and check our numbers. So we already checked the BRs and the 2NOBr. That's good. The N2 on the right side of equation. Whoops, we got to be sure we scratch this out because otherwise you might accidentally use it. Okay? So we have N2 on the left side of equation 2a and on the left side of the target. Same with O2. And everything else checks out. The two NOs, I should have canceled those. 2NO on the right side of 2a and on the left side of equation 1. So they cancel. So everything checks out. So now by adding these equations, what we're doing is multiplying 2 times this number right here. And that gives us about 9.5 times 10 to the negative 31st. That is a tiny, 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 crazy small equilibrium constant, that means in this target reaction, this reaction basically won't happen. You'll never have these reactants move over to products there at that particular temperature. It could be different at a different temperature. They're just going to stay as N2O2Br2, and they're not going to combine to form to NOBr. That's what the very tiny Kc tells us. None of the reactants, virtually none of the reactants are going to turn into products. Okay, now we're not done with the problem. It's asking us to convert it to Kp. So we had that formula. Okay, so Kp and now we plug in our numbers. So there's the Kc, it's what we just calculated. And they did give us a temperature here, which I should have written down. Write down any pertinent information. It's 298 K. And then I'm going to use square brackets in place of double parentheses. And the change in moles. So the change in moles of the target is, you have 1, 2, 3 moles on this side and 2 moles on this side, so it's -1. So we're going to multiply 0.0821 times 298 equals, that gives us 24.47, and then we're going to raise that to the exponent of -1, and that gives us 0.04. And now we're going to multiply that by 9.5 times 10 to the -31st power. And that gives us an even smaller number for Kp. Times 10 to the -32nd. Okay, one more to go. It's 15.29. Okay, so let's bring it over here and read it. And it says, it's right there. It says the equilibrium 2NO plus Cl2 produces 2NOCl is established at 500 K. And just saying that the temperature is not going to change. An equilibrium mixture of the three gases has a partial pressure of 0.95 atmosphere, 0.171 atmosphere, 0.095 atmosphere, 0.171 atmosphere, and 0.28 atmosphere for NOCl2 and NOCl respectively. Again, what that means respectively is that the 0.095 corresponds with the first reactant here, or the first compound. The second number, 0.171, corresponds with the Cl2, and the 0.28 corresponds with the NOCl. That's what the word respectively means. Calculate Kp for this reaction at 500 Kelvin. Okay, so we're going to go ahead and write down the equation. Alright, and what we have is pressures. So the way you write pressures are the capital letter P and then subscript it with whatever the compound is. Okay, alright, so it says an equilibrium mixture, so they're already at equilibrium. You don't need to use a rice table here, because you use a rice table to figure out what the equilibrium values are. We already know the equilibrium values, so they made this question a little bit easier. So now all you have to do is write the law of mass action and plug the numbers into that. So let's go ahead and do that. So Kp, okay, products on the top, coefficient becomes exponent, reactants on the bottom, coefficient becomes exponent. Okay, exponent of 1 on that one. So now we just plug in numbers. So for NOCl, it's this. And we have to square that. NO. And we square that. Cl2. And now we just calculate. Again, I like to kind of do things 0.28 x squared, and it gives us this on the numerator. In the denominator, 0.95 squared times 0.171. This. So our KP value will be simply that division there, and it gives us this. Pretty much 0.5. We call it 0.51. Okay, and I made an error on my calculator, which is why I like to do it this way and write down numbers, because if that happens, I can go back and check and see what I had compared to what I put in. If I try to do it all in one step and I don't write it down, then I'm kind of lost. So 0.95 squared, let's do that again. It's 0.095 squared times 0.171, and that gives us this. I was off by 2 entire decimal places. 0.01543. Okay, so now we can do this division problem. And that gives us an answer actually of not 0.51 but 51. So I was off by 100 times. Okay, so there is the answer. But again, it illustrates why, in case you're wondering, do I actually do these problems here, or am I just copying from an answer book? The answer is no, I'm actually doing them here. So anyway, it's why I like to write down, do the problem in pieces, and keep a track of what I got with each step like that, rather than try to do it all at one time. Okay, that takes care of this assignment. This is the first one. And next you go on to learning about rice tables, and those are incredibly important when we get into acid-base reactions after the break. So we'll see you on the next lesson.